This is the second video of the topic SFD and BMD. In the first video, I explained how to draw the shear force and bending moment diagram of different types of beams. In this video, we will discuss how to draw a shear force and bending moment diagram of different beams under different types of loading conditions. So in the first video, I explained the process to draw the shear force and bending moment diagram, which is the very first step was to find out the reactions at the support. The second step was to draw SFD with the help of the loading diagram, and the third step was to draw the bending moment diagram with the help of shear force diagram. So first find out the reactions, then with the help of loading diagram draw the shear force diagram, and with the help of the shear force diagram we will draw the SFD, the bending moment diagram of the given beam. So let's start with the first question. Here we have the cantilever beam, which is having an external moment of magnitude m0 at the free end. Let this point is A and this point is B. So we need to draw the shear force diagram and bending moment diagram of this beam. So the first step, find the reactions. So there is one external moment m0 at the free end, therefore at the fixed support we will have one reaction at the support of the same magnitude m0. Moment reaction is m0 at the support, whose nature is in anti-clockwise direction. Because the external movement is in clockwise direction, therefore the reaction will be in anti-clockwise direction. So the second step is to draw shear force diagram. So to draw the shear force diagram, first we draw a horizontal line having length equal to that of the given beam in question. So at point A we have no reaction force, so the shear force at this point is 0, and in the whole beam there is no transverse force. In the whole beam there is no external force nor reaction force, so the shear force is 0. So this is the SFD. Shear force value is 0 in the whole beam. Now to draw the bending moment diagram, draw length equal to that of the given beam of points at point A and B. At point A we have external movement in anti-clockwise direction. So it will shift the bending moment diagram downward with magnitude m0, and in the whole beam there is no external movement up to point B. There is no movement, so there is no change in the bending moment diagram, and at point B there is a clockwise movement of magnitude m0. Therefore our bending moment diagram will shift upward by magnitude m0. This is negative, and this is our bending moment diagram. So in 2 to 3 minutes we draw the shear force and bending moment diagram of this particular beam. Now let's move towards the second question. In the second question we take a simply supported beam having roller support at left end and the hinge support at the right end, there is an external movement of magnitude m0 whose nature is clockwise direction at a distance of A from left support and B from right support. We have to find the shear force and bending moment diagram of the beam. Length of beam is A plus B, obviously. So first step was to find the reactions. The first step was to find the reactions. So the external movement is in clockwise direction. Look, the external movement is in clockwise direction. So the reaction movements will be opposite, means in anti-clockwise direction. So at this point the force is in upward direction, and at this point the force will be in downward direction. So the reaction diagram would be like this. At this point we have external movement m0 in clockwise direction, so our reaction force will be in anti-clockwise direction. Curl the finger in this direction and we will get the anti-clockwise direction reactions. So what is the magnitude? Magnitude will be equal to m0 upon A plus B and m0 upon A plus B. Look, these reactions have to balance this external movement at this point having magnitude m0. So the couple will be force into distance between the couple, which is m0 force, and the distance between the couple means m0 upon A plus B. This is the value of force, and the distance between the couple is A plus B, which will again give m0 and in anti-clockwise direction. So this particular forces will balance this external movement. Okay, so we got the reactions of magnitude m0 upon A plus B in upward direction at right support and in downward direction at the left support. So now let's draw the shear force diagram of that particular beam. Draw the horizontal line equal to the length of the beam and we see that at this point we have a downward reaction, so our shear force diagram will move downward by magnitude m0 upon A plus B. And in the whole beam, let me first draw the beam, which is this m0. We have downward reaction, we have this at this point upward reaction. Magnitude will be m0 upon A plus B, m0 upon A plus B. So we have downward, so our bending moment diagram moves downward by amount minus m0 upon A plus B, and in the whole length there is no other external force. Therefore the shear force diagram will remain constant. At this point there is upward force of the same magnitude. The nature is negative. So this is our shear force diagram of the beam. Nature is negative. Okay. Now let's draw the bending moment diagram of the beam. Let's draw the length, horizontal line equal to the length of the beam again. At this point, left, extreme left point, we have no external movement, so the movement at this point is 0, and the nature of the shear force diagram is negative and constant. So what is the graph of negative and constant? The graph of negative and constant is this theta remains constant everywhere. This is the graph of negative and constant. So our graph will go down by negative and constant. What is the magnitude of bending moment at this point? It is this area. It is this area, means minus में m naught into upon a plus b, this is the vertical length, into horizontal length is a. So this is the value of movement at this point. Now we have a clockwise movement at this point. So I told you that the clockwise movement will shift the bending moment diagram upward, and anti-clockwise movement will shift the bending moment diagram downward. So the clockwise movement will shift the bending moment diagram upward. First we find the magnitude, so that we can know that the movement at this point is negative or positive, and then accordingly we will draw the point. So minus m naught upon a plus b into a upward means plus, what is the magnitude of external movement? It is m naught. So this will give the value of minus m naught into a plus m naught into a plus b upon a plus b is equal to m naught into b upon a plus b. M naught into b upon a plus b, and it is positive, so our bending moment diagram is positive. What is the value? Value is m naught into b upon a plus b, and then what is the nature? It is negative and constant. Again the same graph, which is negative and constant. So this is our bending moment diagram, whose this side is negative and this side is positive. So what is the conclusion? From bending moment diagram we see that the beam has variable bending moment whose left portion is subjected to negative bending moment and right portion is subjected to positive bending moment. So this is the shear force diagram, and this is the bending moment diagram of that beam, of that particular beam. Now let's move towards the next question. So these are some very good questions of shear force and bending moment diagram. P3. In this third question, there is a simply supported beam having roller support at the left side and a hinge support at the right side. Okay, this beam is subjected to a uniformly distributed moment having nature anti-clockwise. Having nature anti-clockwise and magnitude m naught kilonewton meter per meter. This is a uniformly distributed movement. This is a uniformly distributed movement having magnitude m0 kilonewton meter per meter. So let's draw the shear force and bending moment diagram of this beam. So first of all, find the reactions. So what are the reactions? This is the beam. The external movement direction is, again, look at the direction of fingers properly. The direction of external movement is clockwise. Direction of the movement is clockwise. So the reaction will be opposite to the external movement, means in anti-clockwise direction. In anti-clockwise direction, so at the right support the reaction will be in upward, and at the left support the reaction will be in downward. Okay, these are the direction of the reaction forces at the support. Now what is the magnitude? These two reactions has to balance the total moment of m0 into L. L is the length, okay. L is the length, m0 into L. So, and this is the length. So this is m0 and this is m0. Let's check. m0 couple value is force into distance between them, m0 into L, and we have to balance this is equals to m0 into L, means these two reactions will balance the external movement. Okay, this is the reaction diagram of this beam. Now let's draw the shear force diagram. To draw the shear force diagram, we draw a horizontal line equal to the length of the beam. At this point we have external downward reaction force, so our shear force diagram will move downward, and the magnitude will be the magnitude of the external force equal to m0. We first draw a horizontal line, then at this point we have an external reaction downward force, so our shear force diagram will move downward by magnitude of m0, and in the whole beam there is no other external force. We have external movement but no external force, so the shear force diagram will not change. At this point we have external upward shear force, so our diagram will goes up by magnitude m0. The nature is negative. Now let's draw the bending moment diagram of the beam. To draw the bending moment diagram, I again draw the horizontal line of length equal to length of the beam. Now at this point we have external movement, and in the whole length of the beam we have external movements. And I told you that in first lecture that dm by dx is equal to v. This particular relation means slope of the bending moment diagram is equal to the shear force. This particular relation is not valid for external movement. This particular relation is not valid for external movement. So what we do, we will go for the basics. So what is the basic? That bending moment, at any section is equal to the summation of movements either to the left or to the right of that section. So let us find the bending moment at this point. At a distance of x from the right support. To find the bending moment at this point, we find the external movements. We find the external summation of external movement to its right. So what is the summation of external movements? Is bending moment at x to the right is equal to, this is m0 force, it will act in this direction, m0 m naught into x. Where is x? X is this section at a distance of length x. M naught into x minus m naught. M naught magnitude of UDL, UDM actually, magnitude of UDM, m naught into x minus में m naught into x. So this is 0. So bending moment at XX section is 0. Means the bending moment diagram will not change. So this is the final bending moment diagram, which is a straight line. What is the conclusion? Bending moment for the whole length of beam is 0. So it is a very good question. Let us move towards the next question. In this question we take a cantilever beam of length L carrying a uniformly varying load of maximum magnitude W acting at the center point. This is in downward direction, that this point is B and this point is A. This is a uniformly varying load of magnitude of maximum magnitude W acting at the center point. Now first we find the reaction forces at the support. So to find the reaction forces, we convert this whole uniformly varying load into a single point load acting at the centroid of this region or this triangle. Okay, again, so to find the reactions, we convert this uniformly varying load into a point load of magnitude of this area of triangle acting at the centroid of this area of triangle. Let us see, this is the beam. We assume that this UVL is converted into a point load acting at the centroid point. This is the centroid point. What is the magnitude? Magnitude is the area of this triangle. Half base into height means WL by 2. This is L by 2 and this is L by 2. So what is the reaction force at the support? It is in upward direction, WL by 2. And this force will cause a clockwise movement at the support. So the reaction will be in anti-clockwise direction of magnitude WL by 2 into L by 2 is equal to WL by 4. So this is our reaction force at the support and this is our reaction moment at the support. Now let us draw the shear force diagram. To draw the shear force diagram, we draw a horizontal line equal to the length of the beam. At this point we have an external reaction force of magnitude WL by 2. So our shear force diagram will move up by magnitude WL by 2. And then what is the behavior? So this diagram, look, this diagram is only useful to calculate the reactions. Now to draw the shear force and bending moment diagram, we repeatedly look at this diagram only. Okay, so what is the behavior till midpoint? It is the force is negative and increasing. The force is negative and increasing. So what is the graph of negative and increasing? It is like this, negative and increasing. Theta is increasing and is negative. So till the center point it is negative and increasing. What is the magnitude of this point? Magnitude will be WL by 2 minus the area of this triangle. Area of this triangle is half base into height. Half base into height. So WL by 2 minus में WL by 4 is equal to WL by 4. So the magnitude here is WL by 4. And again from this point the behavior is negative and decreasing. It is the graph of negative and decreasing. This is the graph of negative and decreasing. This is positive. Now to draw the bending moment diagram, we again draw horizontal line equal to the length of the beam. At this point we have anti-clockwise movement. So anti-clockwise movement will shift our bending moment diagram downward by magnitude WL square by 4. And the nature of the shear force diagram is positive. It is positive and decreasing. So what is the graph of positive and decreasing? This is the graph of positive and decreasing. Theta is positive and it is decreasing. So till midpoint our bending moment diagram is like this, positive and decreasing. So what is the magnitude at this point? To find the magnitude of bending moment at this point, we go by fundamental. Like we find the magnitude of the external movement to the right of this section, means the area of this triangle, and its distance from this point. Okay. So it is W, this point is say B, this is L by 2, this is L by 2. So we assume that our load is converted into a point load of magnitude of this and at the centroid of this triangle. So the centroid which will be at L by 6 distance from this point. Centroid of the triangle is H by 3 from this side. So here H by 3 means L by 2 by 3 means L by 6 from this side, and the magnitude is the area of this triangle, means half into base into height, means WL by 4. So what is the moment? Mx is equal to WL by 4 into distance, means L by 6 is equal to WL square by 24. So the value is WL square by 24. And again, to draw the shear bending moment diagram, what is the nature of SFD? It is positive and decreasing. Positive and decreasing. So same graph, but the slope is different. Okay, starting slope is different. This is negative in nature. So this is the bending moment diagram, and this is the shear force diagram of this beam, this particular beam. So this is the completion of second video. If you like this video, please comment, please like the video and subscribe this channel. And in the next video I will tell you how to solve the questions of internal hinge and propped cantilever beam. Thank you.